Yeah, what was the question?
On the, for WebAssign, are you going to be pushing everything forward from this point back a week, or would next week we just have forward?
No, anything that would have been due this week, I'm pushing to next week.
In addition to the ones that are normally due?
Yes. I mean, we'll change accordingly.
So everything's pushed back a week.
Everything this week is pushed back next week, but otherwise we're sort of going with the pace that I'm on. That only applies to WebAssign, by the way. So the written homework I expect you to do right away. Yeah, so today we're finally going to start to do some calculus. It's going to be so amazing. Yeah, so we've been spending, we did like a week and a half on algebra and pre-calc, right? So I mean, we're sort of getting boring. It's good that we're going to be able to get out of algebra and pre-calc today. So what we've looked at some of the, how to simplify some trig functions and things like that. We've mostly focused on functions so far, which, as you might have guessed by now, is a tool in mathematics to really model some sort of relationships that we see in real life, right? And we all know what a model is, right? So you try to describe a real life situation in mathematical language so that you can solve problems, make predictions, optimize things, right? So you sort of use math to work in the real world. And the function was mathematics' attempt to cover the dependency relationship, right? When one thing depends on another thing. That's what we do in Calc 1 and Calc 2. In Calc 3, you're going to have one thing depending on several things. If you do linear algebra, you're going to have several things depending on several things. But for now, we were trying to capture the dependency relationship with functions. And we can actually, by doing that, answer a lot of questions, right? Once we can map certain things with functions. So things like, temperature versus time. The weatherman gives you a forecast. He says, by this time of the day, it's expected to be this temperature. That time of the day, it should be this temperature. Or distance versus time. At this time, the car, or the train, or the plane will be at this position. At that time, the car or plane will be at that position. So there you can sort of think of time as an independent variable, and your distance or location or any of that is the output variable, the dependent variable. And so if you can sort of replace all these objects with variables, you can answer questions about the situation. However, this has its limits, right? So, no pun intended. There are other questions that we'd like to answer that functions just don't give us the capability to answer. In particular, life is always changing. Things are always in motion. It's very important for us to be able to capture this notion of change, right? How fast something changes. Sure, in my bank account at this time I have this much money, but what's the interest rate? How fast is it growing, right? How fast is it moving? That I can make plans down the road for where my money will be, right? I don't just want to know about it at a certain time, but sometimes you need to know how fast things are happening, what is changing, how it's changing. And just having a function on its own is actually not good enough for that purpose. We have to somehow find something that captures change, the change of a function, the rate of change of a function, how it changes over time. And that's what about half of calculus is about, the rate problem, right? This idea that we have to somehow figure out how to deal with the rate. So it's called the rate problem. And calculus's answer to the rate problem is called the derivative, right? Basically, if you boil down the rate problem to math, like at its essential core, basically figuring out the rate problem amounts to being able to draw tangent lines to curves. So a random curve, I think a random point, can I draw a tangent line, which is a straight line that touches the curve at that one point locally, right? Being able to figure that out is exactly the same as figuring out the rate at which the curve is changing at that point. So if this curve actually means something in life, like your bank account or something else, you can figure out how fast it's changing at any given point by finding a tangent line and finding the slope of the tangent line, which we're going to call the derivative. And we're going to see exactly how we can do this. Another major problem that calculus seeks to answer is the area problem. Right? So not only do we want to know how fast things change, but sometimes you're going to want to know how to compute area. If you have a rectangle, it's pretty easy, but what if you have this weird shape, right? Let's say that shape represents your territory, right? How much land do you own? How do you know exactly how much land you own? You want to find out the area of land that you own. Well, one way you could possibly do that is, since you know how to find the area of rectangles, you just divide this up into rectangles, right? Sure, when a rectangle is completely in the shape, you know the area it covers, but what about these guys at the ends, right? That are not fully rectangles. How do you estimate those? Not the derivative, right? It's actually, you want to find the area. So what you can do is you can start making this one into rectangles, and then you still have guys at the end. How do you approximate those? Well, you make more rectangles and you keep going, right? But obviously you can't just sit there forever cutting things into smaller rectangles. You have to find some way to get to the exact answer in a very systematic and efficient way. And the second part of calculus deals with this problem. And the tool that we use for this problem is called integration, right? Or the integral. Integration is called a method. So these are the two basic things that calculus deals with. But neither of them could work without the notion of a limit. You see, how we figure out how to draw a tangent line is we draw another line, and then another line, and then another line. And we start getting closer to the tangent line. Turns out that drawing these other lines are a lot easier than getting to the tangent line. But we start off somewhere, and then we start to get close to what the answer should be. Same thing that we were doing with areas, right? We started with a general approximation, but then we started getting closer and closer to the area by starting dissecting more and more. Right? This idea of getting close to something is what we can capture by the limit. The limit talks about getting close to something. So really the derivative and the integral, they can't work without the limit, because the limit is what makes them work. It's like the Higgs boson of calculus. It's a really important topic, and I know it happens in chapter 1 and 1.3, and you might overlook it as not very important, but it's actually super important that you can find limits, because it's what's going to allow us to do all the things that we have to do. And you might also know that, obviously these considerations haven't been here since yesterday, right? Man has been orbiting the land for thousands of years. And calculus has been done for thousands of years. I mean, Archimedes could draw tangent lines to curves, and he could also find areas for random shapes, right? Archimedes lived 200 BC, right? So 200 years before Christ, this stuff was happening. I mean, we could figure out ways to do it. But as far as calculus as we're doing it now, the formal treatment, the modern treatment of calculus is due mostly to two guys called Isaac Newton and Leibniz, right? And they sort of, not only did they formalize how to do this, guy gave us all the notation we use and how to do these things very systematically and formally, but they actually developed something called the fundamental theorem of calculus, which actually connects these two areas of math, right? It seems like the problems are very different, but they're actually two sides of the same coin. There's a fundamental theorem of calculus that says finding the rate is sort of the opposite process of finding the area. And that's what the fundamental theorem of calculus is about. And we have Newton and Leibniz to thank for that. But again, none of it could be possible without the notion of a limit. So the limit is what we're going to start our discussion with. Calculus is the study of limits at the end of the day. This is the study of derivatives and integrals, and they all depend on limits. So in Calc 1, we're going to mostly deal with this problem. In Calc 2, you're going to deal with this problem. Right? We'll touch a little bit on this problem at the end of the course, but not much. Mostly we're going to be able to figure out how to draw tangent lines and how to apply this to solve problems. Okay? So that's just an overview of where we're going in this course. And our journey starts with the limit. So let's start there. What is a limit? We say a function f of x approaches a value L the limit as x approaches a of f of x equals L if the following happens, right? So we want to capture the notion of our function getting close to something when our x value is getting close to something else, right? This is the notation that we'll use to capture that, and this is actually what that notation means. That's a mouthful. This is called the epsilon delta definition of a limit. Basically, it's saying that when your x values get close to something within a restriction of delta, then your y values will get close to something within a restriction of epsilon, where epsilon is any given condition that you're given. But it's sort of too complicated for our purposes. This is sort of the definition that math majors will work with. We're not going to work with that definition very much. We're sort of just going to skip over this stuff and just basically say we write limit as x approaches a of f of x equals L if there is, if as x approaches a, this just means x approaches. Right. Have you guys seen this symbol before? This arrow.
Yeah.
Right, it just means x approaches a, it gets close to a. Right? If as x approaches a, then your f of x approaches L. That is, the limit is the value So limit just basically means the y value get close to when your x value gets close to something. That's basically how we're going to think of it. Let's do an example. So I see confused faces. Alright, let's look at this one. What if I ask, what is the limit as x approaches 1 of? Now I'm going to take my function to be 2x plus 1. What do you think the answer would be?
3.
The answer would be 3. Right? This here is my f of x. Now as my x gets close to 1, notice that this value will get close to 3. Right? Since when x gets close to 1, 2x plus 1 will get close to 3. We can also do this pictorially. Right? So you know what 2x plus 1 looks like. That's just a straight line going to here at 1. Here's your x value 1. And you want to know when your x value gets close to the value of 1, is your y value getting close to some value? And it turns out, yes, it gets close to the value 3. Now it turns out in this case you can just plug in the 1 and compute that. But you won't always be able to do this. But this is sort of the notion that we're going to go for. Okay. So basically, this means the following, right? As your x gets close to 1, this expression will get close to 3. Right? That's the idea of closeness that we're talking about. And we actually don't require that this guy be in the domain of your function. So that's going to be, we're going to talk about that in a bit. But that's basically what we're talking about when we talk about limits. What else do I want to say about limits? How about this one? think the limit is? How did you get that?
X plus 2 x minus 2 on the top. And you cancel out the x minus 2.
Right. So it seems like here, you obviously couldn't plug in the number just as you could plug it in here, right? Because if you plug in that, you divide by 0. So what you can do is you can sort of simplify this guy to sort of get rid of the problem. And now, you're sort of looking at this function. As x gets close to 2, what does this get close to? Well, the answer is 4. Now, it's very important for you to realize that the function is actually not defined at 2, right? If you actually were to graph this function, it would look like the following. There would actually be a hole where x equals 2 happens. Right? So you're not defined at 2, right? But the limit doesn't care if you're defined. The limit talks about getting close to something, approaching it, right? So you never actually divide by 0. That's a very important distinction. You just keep getting close to 0, inch close to 0, and you watch the y value. What is the y value getting close to if the x is getting close to something? It turns out in this case, the y value will get very close to 4. It'll never reach 4, but it'll get as close to 4 as you want, right? Because you'll divide by 0 if you ever make the y value 4. So that's an important distinction here. Let's look at something else. These are very similar problems that I did on the quiz. Okay. Now, another example. Suppose f of x equals radical x. Find f of x plus h minus f of x over h. And then compute. Let's do this. 4 plus 8. Let's say that was your problem, right? I want to know what this thing approaches when my h gets close to 0. My function is radical x. I create a new function from that function, radical x. And then I'm going to take a limit. What's this equal to?
So how you got 4?
Yeah, that's a 4.
Yeah, how you got,
What is it?
how do you get 4?
I'm giving you.
Radical 4 with h. Yeah, it's like, it's just going on. The next step, the problem. It's the same problem.
Yeah. I'm defining this function.
Yeah.
Oh, can you see?
No,
You're right. You're right.
Is this f of x plus h minus f of h minus f of x?
Okay. Can we simplify this, rationalize?
Yes.
How?
You have to multiply times radical 4 plus h plus radical 4.
Which, right now I'm trying to.
Yeah.
2.
Over 4 plus h plus 2. And then what happens?
You get 4 plus h minus 4 over h times radical 4 plus h.
Right? Because this is the difference of two squares, right? Hopefully you guys noticed that, right? This looks like a minus b times a plus b is equal to a squared minus b squared. So you square this term, you square that term, and write them down. Now what happens?
Now you
4's go away.
You get 1 over.
And then you can cancel the h's. You get 1 over the radical 4 plus h plus 2. Right? I asked a very similar problem to this on the quiz. So that's how you continue. Now, given that expression, if I want to find the limit as h approaches 0, f of 4 plus h minus f of 4 over h. That's just the same as asking the limit as h approaches 0 of this thing. Right? Now before, notice that I could not let h get close to 0 because I was dividing by h. I don't know what division by 0 means. So just as in this case, I try to simplify it by rationalizing. So now I can actually make h get close to 0. What would this get close to if h gets close to 0? Right, this will be 1 over radical 4 plus 2. This is 1 over 4. Now this 1/4 actually means something, but we're going to see that a bit later. I just want you to get into the idea of how these limits work. So you'd love to be able to plug in the numbers, but you can't always do that. Sometimes you have to simplify, and you just have to realize that sometimes it just doesn't exist at that number. But limits don't care about existing at the number, it just cares about getting close to it. Yes?
Is that a relation to this part, or you're finding the limit here, and here you just solve it?
I asked 2 questions. This was like part A and then part B.
So I don't understand what you did here. It's less than 0. It's like
Here I just computed this,
Okay.
right? And I simplified and I got to that.
Okay.
And then the next step I said I wanted to find the limit as h approaches 0 of this one. So that's what I did here.
You plug in 0?
Yeah.
Right, I couldn't in the beginning because I divided by 0. But after simplifying, that was no longer a problem.
Okay.
So now I can literally just plug in h equals 0.
Okay.
Right? And you get that. There is also the notion of one-sided limits. We're going to come back to this in a bit as well. If I say limit as x approaches a, and I put a little minus sign here of f of x, this is called a limit as x approaches a from the left. Right? When I say limit as x approaches a, and I put a little plus sign here, f of x, this is equal to limit as x approaches a from the right. Now, the reason why we break things up like this is because they're not always the same number. Example. Let's look at this one and this one. Let's look at the graph so we can see it. You don't have to do the graph, but I think it's very enlightening to do the graph. What does y equal radical, what y equal absolute x over x look like?
Upside down D.
Just going down to a line.
Positive and negative.
Where's the positive one, where's the negative one?
At the 0 or
The absolute x would be broken down into positive x and negative x. And we divide them.
Right, you know that this is just x over x when x is greater than 0, and I think it's minus x over x when x is less than 0. At 0 we can't be equal. So here, It's 1 when we're positive. It's -1 when we're negative. Right? So the picture looks like that. Now, if I try to figure out what is the y value getting close to when x is getting close to 0, but from the left side, what would the answer be?
-1.
Well, here's 0. I want to approach 0 from the left side. Right? What is my y value getting close? If I'm on the curve approaching 0 from the left side, what is the y value? -1. Right? However, if I approach it from the right, it means I'm on the curve, but I'm on the right side of 0. If I'm approaching 0 from this direction, I get +1. Right? So here's a question for you. For the same function. So if f of x equals f by x over x, what is the limit as x approaches 0 of this guy?
Doesn't exist.
Correct. It does not exist. You call it D and E. Or does not exist. Can anyone explain why it does not exist?
The right term is negative, the left term match. That's right.
So why do we care that they don't match?
So the limit approaching from the right and the limit approaching from the left is different. So it's not the same.
They don't come close. They don't come close.
Well, what is the limit?
They don't end up with the same results.
Yeah, they don't end up with the same result.
They don't end up with the same results. That's why.
No, not always. We did examples where we have 0 in the denominator and it wasn't working.
Because the limit from the right and the left is different. One is
Why does that matter based on the definition?
Because when you come from the left, it's approaching more towards negative infinity, and when you come from the positive,
No, the approach is -1 and positive. Because remember, the limit is
getting
the
next
y
to
value that you get close to when your x value gets close to something, right? So if someone asks you, what is the y value you get close to when x gets close to 0? -1. No, it's 1. No, it's -1. No, it's 1. No, it's negative. There's no answer, right? There is no the y value that you get close to. It depends on your direction. If I come from the left, I get close to -1. If I come from the right, I get close to +1. There is no y value that you get close to, right? So this thing just does not exist. It doesn't make sense in our definition of the limit. Yes? Because the. Right? The limit is the y value you get close to when your x value gets close to something, right? Remember the notion of a function, you have to know what your output is.
so it's like whenever you come from positive and negative, whenever you have two different answers, it does not exist.
It does not exist. They have to match up. You have to approach a single y value when your x value is approaching something.
Is the only way to figure out the limit to graph it, or is there another way of graphing?
No, you could see it here as well. Just by writing the definition. This is actually the function 1, x greater than 0, or -1, x less than 0. Clearly you have two different functions here. So you can do it this way, but I thought graphing the picture was very, very nice thing to do. Okay? So now, let's do another graph. And let's see if we can figure out what the limits will be. It's very similar to the quiz, and it's the one I asked you guys in class today. Let's look at it. Let's finally look at this guy. 1, if x is less than -2, equals 3, if x is -2, x plus 3. 3 minus 1 over x squared. 1 over x. 1 over 2. So first, let's graph this. Probably gonna want more space. I'm gonna ask some questions on the picture. Okay, so how do we actually graph this? Notice the x values that we're talking about are we're at -2, -1, 1, 2. Okay, so we describe a region less than -2, so what do? We look at everything less than -2 going back, right? And what is our function? Function 1, which is just a horizontal line, which we make 1 here, right? Strictly less than, so I leave an open circle. Now, at -2, what is my function? 3. Let's say I'm at 3. Okay. Between -2 and -1, what is my function? X plus 3. So where is it on the -2 line? Right, you can plug in -2, right? Plug in -2 here, -2 plus 3 gives you 1, so it actually overlaps with this one, right? Where is it on this endpoint? It's at 2, so you just plug in 2 into that. Plug in -1 into this, and you get 2. So, and you know it's a straight line, you just connect the 2 points, right?
Why is -2?
Come again?
Since -2 is less. Should be.
It's not more than.
Did I? Oh. Yeah. Right. It wouldn't be a function if it was true, right? Okay. So now 3 minus x squared. How does that look?
You simply plug in it.
How does 1 over x squared look?
Like the graph of log.
No. It looks like this, right?
Oh yeah. Oh. The even and the odd numbers.
So then if I look at -1 over x squared, what does that look like? Upside down. Now if I look at -3 minus 1 over x squared, what does that look like? The same thing, but it's shifted up 3, right? So here the level was at 0, so now it's at 3, right? So this is just the graph I'm drawing. And it would start where? So notice if I plug in -1 into this, I get 3 minus 1. So it actually starts on this point, which is 2. And then I just...
Plus, it will be plus. Oh no. Sorry.
Right? And then on the other side, it would still be at the level 2.
So didn't you say you start off from 3?
What starts from 3?
The graph, because you shifted up 3.
Yes, but I cut it off. The graph would continue to do this. Right? But I don't care about that region. I want to cut it off at -1. At -1, I just plug it in here and find it out. Right? So I know here the y value is 2. And at 1, I plug it in here and find the value. And that would be 2. Right? So if you want to know where to stop graphing, you just plug in the endpoint so you know how far you have to go.
So whenever you plug it in the number, whatever number you get,
That's the y value that you start at. Yes. Right? And what about 1 over x? What does 1 over x look like? Right, like that. Right? Now clearly we only want this side, because we only want it to be between 1 and 2. So now at 1, where is it? It's at the y value 1. Is it shaded? Yes. At 2, where is it? It's at the value 1/2. Is that unshaded? Yeah. And then I just draw that sort of curve. Now, after that, for greater than 2, I'm just equal to the constant value 1/2 forever. Right? So this is what the graph looks like.
I have
Yes?
a question about x plus 3 and 3 minus 1 over x squared.
Yeah?
If x is less than or equal to -1 for the top one, and then the one below it, -1 is less than or equal to x, what may overlap?
What would overlap?
The points. When they overlap at -1, 2.
Okay? Yeah? But what's the problem?
That's what they're like, because
Yeah, I still have a single x value. It's still minus 1 in both cases, right? It's still x equals -1 only maps to the y value 2 in either case, so it's fine. Right? If I had another point on the same level below or above it, that would
that's
be
what I was
bad.
thinking of.
Right, but they both overlap, both coinciding is fine. Yes?
Where do you cut off the middle lines? Where do you cut off those lines?
These lines,
Yeah.
I cut them off wherever the endpoints tell me to. So I literally plug in the endpoints into the function and figure out where the y value stops.
No, I mean for b minus 1 over x squared. You just cut it out because you're going forever. So where does it end?
Same thing. Just plug it in.
What do you mean? This? These?
Yeah.
No, they go down forever. You can never
Negative
actually touch
That's
0.
negative.
Yeah, they go down to negative. Keep going forever.
Yeah,
It's called asymptote. They get closer and closer and closer to the y value. You never touch it. So that's what the picture looks like. Now, here are my questions for you to see if we understand what's going on. What is the limit as x approaches -2 from the left? The limit as x approaches -2 from the right? What's the limit as x approaches -2? And for fun, what is f of -2? For this one, what is the limit? I want you to do this for all these points that I put here. One from the left of x. One from the right, left of x. Limit as x approaches -1 of f of x. What is f of -1? Let's also use 0. Technically 0 is in another chapter. Yeah, that's done. I got up to here. Okay, let's do this together. What's the limit as you approach 2 from the left? -2 from the left. 1. As you're on the curve coming from the left, going towards -2, your y value is 1. Okay, what about 2 from the right?
1.
Right, as you're on the curve on the right side, approaching -2, your y value again approaches 1. So what's the limit as you approach 1? Because it's 1.
3.
What's f of -2? 3. What does that mean?
Because there's a point in the curve.
There's that one point that is
There's a point at that point on the
yeah.
graph.
When x is negative 2.
What does it mean for these numbers to be different from that number?
That's approaching, and that's exactly negative 2.
Yeah?
It's not continuous.
Not continuous, that's 1.5. Okay, let's continue. We're going to deal with what this means in a bit when we get to 1.5. Okay, what about this one? 2. From the right?
2.
What is that? The minus
DNE.
one?
No.
It's also 2, right? We're filled in there.
Oh yeah.
Yes?
I don't get it.
Well, this is saying, what is the y value approaching when x is getting close to minus 1 on the left side? Right? This little minus here means the left side. This little plus here means the right side. Right? So I'm on the curve. Here's where x is minus 1, right? On this level. I want to get close to that coming from the left. And get close to that coming from the right. Right? So if I'm looking from the left and I'm getting close to that, what is the y value getting close to when I approach this point? The y value is 2 when x is coming here. If I'm coming from the right side, the y value is also getting close to 2. Okay? You'll see a difference here. How does this work? How does this work?
X approaches from what? Is that negative?
Is that
Yes.
1?
1 from the negative.
1 from the left.
Negative, that's positive 1?
Yes. X approaches positive 1 from the left.
2. It's 2.
It's 2, right? So here's positive 1. My x value is approaching that. What is the y value
2.
getting close to? It's getting close to 2. Right? This one is 2.
1.
Now, if I'm at 1 and I'm approaching from the right side,
1.
what is my y value getting
1.
close to? Well, I'm on the right side of the curve approaching this. The y value is now 1. Right? So what can you say about the limit?
DNE.
Does not exist. Right? Because when I'm on the curve from the left side, I get a different answer when I'm on the curve from the right side. So there is no the y value that I get close to. Right? What is f of 1?
DNE.
It's 1. How do we know?
Oh, because
The shading, oh, the
It's
shading.
filled in here, right? So you know this is the y value that I'm accepting at this point. Approaching 2 from the left.
DNE. It doesn't exist. It doesn't exist.
It's one-sided. No, it's approaching.
Right?
It's approaching. Now it's actually happening.
it's 1/2.
I'm getting to 2, right? As I'm getting close to 2, what is my y value getting close to?
Oh yeah.
Right? Remember, I don't have to actually be at 2. We're talking about getting close to something, right? We don't have to actually get there. Just keep getting closer and closer, right? Now, if I'm approaching 2 from the right, so I'm on this curve, and I'm approaching the right, I also get a half. So the limit is a half. Notice that f of 2 is does not exist. Right? It turns out that points like this are going to be very important later. Whenever this happens for a function at a single point, we say that the function is continuous at that point. If this doesn't happen, we say it's discontinuous at that point. But we'll get more into that into 1.5. Right? Yes?
If you weren't given the graph, how would you find the points?
If you were not given the graph?
If you have points somewhere.
Yeah, you can look at this. You can look at the definition. Yeah. So you can know. Let's talk about that. So let's say I want to do this one, right? But I didn't want to draw the graph, right? So if I'm approaching 1 from the left side, what does that mean? This means x is a little less than 1, right? If you're on the left of 1, you're a little less than 1. So what I'm going to do is I'm going to look for where's my function defined for being less than 1, right? This guy talks about being less than 1. Right? Here's my x is less than 1. Right? So if I'm approaching f from the left side of 1, this is the guy I would look at. And then I just plug in 1 here. Right? And that would be 2. Now if I'm approaching 1 from the right side, that means I'm a little bigger than 1, because I'm on the right side. So I'm going to look, where is x bigger than 1? Well, that's right here. So it means I'm looking at this function, and I plug in 1 again, and then I get 1. Right? Now if I say, what is the limit? Obviously, if the two sides don't agree, it doesn't exist. Now I ask, what is the definition? What is f of 1? Well, I want to look for where it says x equal to 1. Well, that's here, right? This is greater than or equal to. So if I'm looking for equal to 1, I again look at this function. So based on left and right, you can know where you want to look. The function will tell you where you should look. Right? You just remember, to the left means you're a little less than, to the right means you're a little greater than. So you look for those symbols.
What test would you ever ask us to find algebra, or would it all be graph?
It'll mostly be algebraic.
So we find the graph from the piecewise function and then find those values from that graph?
Yeah, I think like on WebAssign you do that. Like I'm not going to say. We're mostly getting to algebra. This is mostly for instructional purposes, so you can sort of see what's going on. Right? We're going to move from graphs to doing things mostly algebraically soon. What else? Yes. It wouldn't be zero. Let me mention that here. So note the limit as x approaches a of f of x exists only. The limit as x approaches a from the left of f of x, and the limit as x approaches a from the right of f of x, both exist and are equal. We will take infinity and minus infinity as valid answers. So, for example, to answer your question, let's say we're looking at these two functions. Right? We're allowing infinity and negative infinity to be answers, right? Even though they're not numbers, right? Because it's instructional, especially when we get to cursive. What if I look at limit as x approaches 0 of 1 over x, as opposed to the limit as x approaches 0 of 1 over x squared? How will we sort of talk about these limits? First, notice there's a problem. There's nothing to simplify to cancel the back terms, right? So everything's getting messed up, right? Notice what the graph looks like. 1 over x looks like this, right? So it means if you're approaching 0, right, you're not getting equal to 0, but you're approaching it from the right side, right? As you're getting close to x equals 0, what's happening to your function? It keeps getting higher and higher and higher and higher. Whenever that happens, you say it's infinity, right? Now, what if I'm approaching 0 from the left?
Negative.
Well, if I'm on the left, we keep going down and down and down and down and down forever. When that happens, we say it's negative. So what can you say about this one? It does not exist. Right? Because positive and negative are different sides of the universe, right? What about 1 over x squared though?
Positive infinity.
If we're approaching from the left, the limit as x approaches 0 from the left of 1 over x squared, you get positive infinity. As you approach the limit as x approaches 0 from the right of 1 over x squared, again, you keep getting harder and harder and harder until that's positive infinity. So for our purposes, we'll think of this as positive infinity. Right? As you start approaching 0 from the left or to the right, your answer just keeps getting bigger and bigger and bigger and bigger. It never actually settles anymore. Which is similarly what would happen here. If I ask you about approaching 0 here, the answer would be negative, right? Yeah. So if you come from the left, you keep going down and down and down. If you come from the right, you keep going down and down and down. But this is really a discussion for 1.6. We'll talk more about that when we get to 1.6. Let's talk more about, that's actually everything we need from 1.3 actually. So the homework for that is due on Thursday. Now in the textbook, it doesn't really do things the way we've been doing. What it actually does, it asks you to plug in numbers, like you're approaching 0, plug in 0.001, then 0.00001. 0.00001, and say, what is the y value approaching? And you sort of do this whole table of values. Yeah, we're past it, right? You have to do it for the homework, but I'm not really going to ask you to do that in class. Basically, what we're going to do to compute limits is what is described in 1.4. We have 10 minutes. And we're going to finish 1.4 in that time. Okay.
Oh my god.
Somebody calls for our website, you know how to
Hey, settle down, quiet. So code C is then the following limits exist. If you take the limit of the sum of these two guys, it's just equal to the sum of the limits. So you can take the limit of the addition of two functions by just adding the limits to them. The limit the product is equal to the product of the limits. Infinity sort of messes up this rule, so it doesn't count if they're infinity, right? So they exist and they're finite numbers. Then the limit of the division of the functions is equal to the limit of the top divided by the limit of the bottom, provided limit of g of x non-zero. Right, so we sort of looked at how to find one limit at a time. This is how, if you're combining functions, how you can find the limits of those functions. constant times the function is just equal to the constant times the limit of the function. The limit of the function to a power is actually the limit of the function raised to the power. Right? Like you can bring the limits inside powers. The limit of a constant is just a constant, right? Because as your x value approaches a, your y value is always giving you the same value, so that doesn't change. The limit as x approaches a of x is equal to a. These are just some important facts. And n here is n here is which means it applies to fractions, in particular radicals, right? So if I have the limit of a radical of a function, it's just a radical of the limit. Well, this one, you sort of apply this one and the product rule at the same time. It's a to the n. I think I should write this down, just so that you guys see it. So the power rule applies to radicals as well. And we actually did this in the very beginning, that first example that we looked at. So let's actually do some more. For example, I want the limit as x approaches 2 of 3x cubed minus 2x plus 1. So this one says, this rule says that because I'm adding things, I can just apply the limit to each thing separately, right? So I mean, you can write this as the limit as x approaches 2 of 3x cubed minus the limit as x approaches 2 of x plus the limit as x approaches 2 of the number 1. Well, this just means you just plug in the 2 here, right? 2 cubed is 8 times 3.
24.
24 minus 4 plus 1.
21.
Right? So this is 21. Technically, you don't have to write this. Like, if you don't write this, I'm not going to care. But you should know that that's what's happening. You know, just apply it to each term. This one, notice that this is, you can take it to be the limit as x approaches minus 1 of 2 minus 3x squared over the limit as x approaches minus 1 of x squared plus 4. This is not 0, right, which is an important thing to happen. So all you do is you take the limit of each, the top and the bottom, and you divide.
Plus,
Yes.
so you break it down into x plus 2 and x minus 2 when
This has to be negative. It has to be a difference of 2 squares. Yeah, this has no 0 as far as real numbers are concerned.
Can you extend it more than that, or you don't need to?
You don't need
But you can, right?
to do what?
Can you do what you did on top?
Yeah, you can write this and limit to each part.
You have to do that?
No. So the limit of 2, yes, it's 2, right? Limit as x approaches minus 1 of this is what?
3. Negative 3.
So it's just minus 3 over, as you approach minus 1 here,
5.
5. So this is just minus 1 over 5.
So you don't have to because you already get the gist of it, right?
Yeah, like, I don't expect you to write this down. You just know in your head that's what you're doing. Just look at one at a time and then figure out the numbers. We'll stop there for now. So 1.3, the homework is due, but 1.4 I didn't finish yet, so. Yeah, 1.3, the homework is due for 1.
The answer to the quiz is online.
Yes.
Yeah, so it's website.
The answer to the quizzes are on my website, which I put in the syllabus.